All right, problems numbers 5 and 6, 27B. Finish them up here. We got a company that manufactures smartphones and their battery life. Battery lives have an average of 30 with a standard deviation of 8. They sell $50 warranty to replace the battery basically if it lasts less than 24 months. You probably had issues with this if you have an iPhone, right? First question says, how many months from the date of purchase is it expected that 25% of the batteries will no longer work? So here's a little picture. We want to know that number right there. So it's just an inverse norm of 25%, the mean of 30, standard deviation of 8, just 24.6 months. So more than a quarter of them, or a quarter of them last 24.6 months. So your cutoff is going to be somewhere in here, right? Which we're going to find out right here. It says one customer purchases the warranty selected at random. What's the probability that they will require a replacement battery within 24 months? So we just want the normal CDF from negative infinity to 24, right? So negative infinity to 24, the mean of 30, standard deviation of 8, it's 22.66% chance. This is how companies figure out their warranties and how much to charge, that sort of stuff. So the next question was, what's their expected values for the warranties? They're going to gain $50 if that battery doesn't wear out, right? But then it says they're going to lose $150 because they're going to have to pay a replacement cost of $200 basically if it does wear out. So this is if it wears out within 24 months, which is that probability, 0.2266. Probability they make the $50 is 0.7734, which is this times this plus this times this. They get expected value of $4.68 for every warranty they sell. Right. So that's it for problem number 5. And the last one here. Now, as you can see, there's a lot going on this one. This may be a little tricky to go over because we got this big chart that becomes pretty important here, so I'm going to try to walk you through it at the same time. But the first question says, Emma is moving to a large city and she wants to know the rental prices of the one-bedroom apartments. She gets a random sample of 50 one-bedroom apartments taken from a website where people voluntarily list their apartments. And then the first question, which is a pretty important question actually, because a lot of times we summarize things based on samples, right? We take a sample. So the first question says, what's the population here? A lot of people just say, oh, it's all the apartments. But it's not all the apartments in the city, right? She took this from a website where people voluntarily listed their apartments. So the population becomes all of the apartments in the city where people voluntarily list vacancies. So it's not all the apartments. We're not judging everything, just the people who list their vacancies. So you got to be careful about what your population is when you take a sample, right? The first question says, next question, sorry, she wants to estimate the rental price. What disadvantage of using the mean rather than the median? Well, you can see by the sample it's really skewed, right? We got this outliers way out here, right? They're going to drag the mean over. It's probably going to look worse than it really is if you look at the mean, so the median is the better way. So the mean will be pulled to the right because of the expensive outliers. Part C says, instead of using the sample median for the point estimate, she wants to use an interval estimate, which makes sense, right? You can't just say, oh, the median is that, because clearly this is just one sample. So we want to figure out, you know, a little bit of an interval instead. So, however, computing an interval estimate requires knowing the sampling distribution, right? So you have to know all the possible samples of a given size. She only has her one sample. So how could she use the information about the rental prices available on the website to develop a theoretical sampling distribution, which is what we do in all these problems, technically, right? So what she'd have to do, which of course she's never going to do it, but this computer did it for us, is she has to take all of the samples of size 50. That's the definition of a sampling distribution, right? All of the samples of a certain size. And then from each one of those samples size 50, she'd have to find the median for each one of those samples. And then she's going to draw her distribution from that. Clearly she's not going to do that, and they introduce you to this idea of what's called, bootstrapping, where a computer does it for us, basically, right? They take a sample of size 50, they find the median, and they do it over and over and over. Instead of doing it for all the samples, because that's impossible, because you just can't decide if you've used them all, right? If there's a huge population, you just do it a lot of times. So they did it 15,000 times. And then they got all these results. So here's where it's going to get a little hard to read here. So the first question, so what they did is they said the medians here and how many times all these medians showed up. They went from smallest to biggest median. And the first question was to find the 5th percentile and the 95th percentile. So to find the 5th percentile, we did this in class too when we had our charts and we used our data, right? The 5th percentile is 5% of the 15,000 scores, so it would be the 750th score. So what I did is I just started up here then, and I started counting until I got to 750. So there's this big chunk here at 2,500, which is 1,899 times. So I wasn't at 750 when I got to the one before it, so 750 is somewhere in that bar. So 2,500 for the 5th percentile. Now we wanted the 95th percentile, I'm just going the other direction, right? So I could do 95th percentile, 15,000 is the 1,425th term, but it's just 750 from the other direction, right? Using that same sense. So by the same reasoning, I go 750 here, there's that big chunk of 700 of them at 2950. So that's the 95th percentile. So now it says, find the percentage of bootstraps, medians, that are in between these two or equal. It's not going to be 95% because of how many there are in those bars, right? So what I did now is that number 408 right there is actually how many numbers there were before I got to the 2,500. The 188 is the number on the other side before I got to the 2,950. So those are the ones that are outside my interval, right? So I added them up, got 596. I subtracted that from 15,000. And I got 14,404. The question was what percent? So the 14,404 out of the 15,000 gives me the 96%. So it's not really a 95th, or it's not really a 95% confidence level, it's really 96% based on that. And they wanted me to write the interval. So I am 96% sure that the median price apartment, based on all these samples, is somewhere between the 2,500 and the 2,950. That's kind of the process for having to do this. If you don't have rules and data like we do, like we have nice rules for means and difference of means and proportions and difference in proportions, so we just use the formulas, but this is kind of the process where those formulas came from. So pretty tricky problem there, but pretty good problem, I think. Cool. That's it for 6.